Previously, most of the wireless providers out there would have used a licensed band. I've dealt with a lot of people transitioning from like 400 megahertz frequencies kind of to the newer frequencies that basically everybody uses for the most part. There's still a lot of licensed band stuff out there, but for most intents and purposes, people have kind of transitioned to the unlicensed or industrial, science, and medical bandwidths that we're kind of showing here. So here's a big table of all the licenses or all the bandwidths, and we're just using the two tiny little slivers, so the 900 megahertz and the 2.4 gigahertz for wireless technologies right now for in the industrial scheme of things. So as I kind of mentioned, we're in 900 megahertz and 2.4. For the 900 megahertz, that's usually focusing on North America and South America. You do have to get licensed in all the various countries there. So it is kind of a good idea to double check that. Sometimes there's some outliers, some countries will kind of break this mold, but for most intents and purposes, 900 megahertz is good everywhere in North America and South America. 2.4 gigahertz will be used worldwide, and you're kind of thinking like Australia, you know, all that sort of stuff. The big kind of difference between the two is in the 900 megahertz bandwidth, you're going to basically, Matt, you can actually hear me, right?
Yes, I can hear you, Jade.
Okay, just double checking because I saw one of the attendees couldn't hear anything. So as I was mentioning, in the 900 megahertz bandwidth, you're actually able to have various powers, you know, larger amount of power going through there than you can in the 2.4 for most intents and purposes. Normally in the 900 megahertz, we're looking at a 1 watt radio, at least for banner. And in the 2.4 gigahertz, we're looking at a 65 milliwatt power. And what that kind of breaks down to is the range that you can get out of these units, as you can kind of see there. So if like for a 1 watt, 900 megahertz, you can get 6 miles clear line of sight with a banner radio. And with the 2.4, you'll get 2 miles clear line of sight with the 65 milliwatt radio. And that'll be pretty common among all the different providers, depending on the power outage. So along with the frequencies, we basically are dealing with the protocols that are on these frequencies also. So there's kind of two major approaches right now. There's one to use a proprietary protocol. So the manufacturer will develop the protocol and use that. The other one is to kind of use protocols that are out there already. So some people might actually create radios in the 2.4 and use the Bluetooth standard and actually have everything be a Bluetooth. Otherwise, there might be Wi-Fi radios where now they're just kind of using the 802.11 and then packaging everything up. Usually when you're using the predefined ones, they'll ensure that everything is set up via encryption. So there'll be like a 128 or 64-bit encryption, something like that, along with those. Whereas with the proprietary protocols, since it's proprietary, it's kind of custom set up. So it's a lot harder for people to figure out what all the information is. For the most part, it'll probably look like noise, or they'll just ignore it. That kind of gets into security, which we'll cover a little bit later. I figured I'd kind of bring that up since we're talking about the frequencies. Do we have any questions on frequencies or protocols?
No questions yet, Jade. We are good to go.
Okay. So for networks, there's three kind of major networks that we're using with the wireless systems. There's a star topology, and basically what we've got there is we've got one master radio that is talking to basically every other satellite device. And every one of those satellite radios has to basically come back to that central location and then the central location will do all the processing and then talk to like your PLC or your data collection system or anything like that. The second system that we're or topology we're looking at is a multi-hop. It's kind of like a tree-based architecture. So you got like your roots and then your trunk basically, and then you're kind of going to all the various branches in the system as it kind of goes out here. So kind of here's like your trunk, and then here's one branch, and then that's branching off to two other branches here. So what that kind of allows you to do is to have a pretty fast system. So you're not limited by if you add more and more radios, it doesn't slow down the system. You do usually have a predefined amount. So like for the banner system in the multi-hop topology, it comes set up to allow for 50 radios, but it can always be expanded up to 99 is basically the limit for it. And we got finally the mesh topology. That's basically where every radio will link to every radio that it can inside of the system. So you'll kind of see how there's these 4 radios that were in range of each other, and they're all linked to all the other ones. So that's great for robustness. This is probably the most robust network. The only downside to it is that the more radios or the more connections you get, it slows down the overall network because there's only so much bandwidth. And you'll get a little bit lower, shorter range also when you go to this. So the 2 type of architectures that Banner uses is we use the star network or topology, and we can do up to 47 nodes with the central unit, so that'd be 48 total. So this and then up to 47 of these satellite units, or what we call nodes in this case. Whereas with the multi-hop or the tree network, we can have up to 50 total by default. That can always be expanded up to 99, as I mentioned. So the another little thing here is in the 2 networks, we use frequency hopping sped spectrum for our our technology in the background. There's really 2 different types. There's also direct sequencing spread spectrum. That's kind of more what Wi-Fi uses, and we'll talk about that here in a little split second. On the star topology, we also use time division multiple access in addition to the frequency hopping spread spectrum, and that allows us to kind of ensure communications goes through very easily. Yes, the nodes or the multi-hop technology can all be used outdoors. There's units that are IP67, and what you really want to do there is ensure that it doesn't actually get hit by a UV. UV is actually the much more of a problem than the weather. So sometimes you maybe just put it under under an eave or something, so that the sunlight doesn't have a direct access to it, because over time the UV will actually damage the circuits otherwise. But that does take some time. I see another question from attendee 72, which is, can the multi-hop form a ring? Well, it's not doing a ring per se. These are all linked together. So if we're looking at, if we send a command to the master unit and we want it to go here, it'll jump through and get there and then come back and follow this path that it's predefined. If, say this connection dies, it can basically remesh itself or reconnect. So this radio could form a link going this direction now and then go back if that's feasible, or just jump back to the main unit if that's possible also. So we have some self-healing capabilities inside of here, and that's why it's a little bit faster than, say, the mesh topology, which is kind of all linked together. So as I mentioned, on one kind of method is a TDMA, or time division multiple access. So some of the more IO-based systems will actually use this. Banner uses it in our star topology. What it allows for is each node in this device, or in this network, will have a little bit of time slice associated with it where it's only on. So what that allows for is you can have tons of different nodes all right next to each other or in close proximity, and one node will turn on, send its communications to the gateway, the next one will turn on, so on and so forth. Otherwise, if we didn't follow this procedure, when there's two antennas really close to each other, say within 6 to 10 feet, you can get some wireless interference, because when they're broadcasting, you don't want the antennas really close to each other. It's kind of like when if you take two walkie-talkies and get their antennas really close to each other and turn them on, you get all that interference. That's basically what happens if you got two 900 megahertz radios broadcasting all the time and really close to each other. So to ensure that doesn't happen, you can use time division multiple access and just give each unit its own little time slice. And even though they're right next to each other, they're not on at the same time ever. And how we do that is when the gateway and the nodes first link up, they basically get a timing chart together and say, hey, you're on at this time, you're on at that time, and sequence up everything. Now, the frequency hopping spread spectrum and direct sequence spread spectrum, these are used in basically all wireless for the most part. There might be a couple other ways to do things, but these are the two most common. So the DSSS, that would be more common to like what Wi-Fi does. So what we're doing there is we take if you got a message, you break it out into little sections, and you put each one of those sections at one of the different frequencies, and you broadcast them in that sort of a method. So you basically scope everything out and ship it out in one chunk. What that allows for is, much higher data rates. So that's why Wi-Fi can do, send video over Wi-Fi isn't a big deal. The other kind of method is frequency hopping spread spectrum. And so what you do is you just take one of those little sections, and instead of, you basically put all of your power just on there, and you put as much smaller data piece of information and transmit it over that smaller band. What that allows you to do is to basically put all your power into that one section, and gives you basically higher noise immunity, and you can transmit further. So it always comes down to, do you want to go further and get less data, or do you want to go a shorter distance and get more data? For most intents and purposes, when we're in the industrial world, we're trying to get analog or digital values, so it's very small amounts of data for all intents and purposes, and we want to make sure that that data gets from, say, the PLC to the central data collection area. So we want to be able to have the higher power, which will let us get through around obstructions or bounce the signal around, and that where there could be a lot of obstructions in the manufacturing plant. So using the frequency hopping spread spectrum makes a lot of sense in that case to ensure we get the information there. Now, if you were trying to, like, say, move information from a PLC to, say, a remote HMI, or you wanted to pull the HMI screen back to another location, then it might make more sense to use some radios that have direct sequence spread spectrum, because you're going to be moving graphics around, and that takes up a lot of bandwidth. So that makes more sense to use those sorts of radios when you're trying to do that. So here's kind of another little graph showing basically the same thing. You can see the time versus the frequency on the direct sequence spread spectrum. And basically, you're just getting a big bar going across there. Whereas on the frequency hopping, you've got little time sections where you're just on one frequency at that specific time, and then you jump to another one. So Matt brought up, does DSS have more issue with interference? I mean, they both. I mean, if there's a wireless interference going on, you could lose like say one channel has a lot of interference going on, you might lose that channel, and then the protocol level takes care of that by shipping it multiple times, so you kind of slow things down a little bit that way. Whereas with the frequency hopping, since you're jumping around the various spectrums, the various bands, I should say, if one of the bands is blocked at that point in time, you'll be at a different band the next time it comes around to send the information. So you don't really have to kind of worry about that quite as much. It just may take you a couple extra transmissions to get the information through, whereas on the DSS, you have to let it the protocol where it goes, hey, I got like say 9 out of 12 of the piece of information I want. Now I need to get kind of the extra 3, and it kind of shifts things around to get that information there. So Matt also asked, how fast do the hops happen? So in the star topology system, if we go back a couple slides, it depends on how many units are in the system for what your update cycle is. So like for 8 nodes here, that's going to be a 62.5 millisecond update cycle. Whereas in 16 nodes, it's going to be a 125 millisecond update cycle. So in there, you can kind of predefine how fast the system is going to be. In our multi-hop system, let's see here. I want to find a good picture. So if we're using our multi-hop system, the jump from, say, one location to another takes 40 milliseconds. So if we were going all the way down here, it'd be 80 milliseconds this way and then 80 milliseconds back for a round trip time of 160 milliseconds. So having the least amount of hops is preferable if you're worried about timing. But if you're trying to go over large distances, this is where the multi-hop technology shines. If each hop is, say, 3 to 5 miles, now you've gone 10 miles, where in a star topology system, you're limited to only one location. Oh, I see what you're saying now, Matt. How much time between frequency hopping? So for the most part, it's jumping every 20 milliseconds, as it's shown here. That's for Banner. If it's other companies, they may have that set up to a different number, so that'll be predefined by the manufacturer. So when we're really doing the frequency hopping, I don't know if I covered this. We use a hop table. So when we're first connecting, we send these hop tables to the various nodes, and basically the main unit, either a gateway or a master radio in the Banner system, will have these tables inside of it, so it knows to be on which frequency at which time. So it's kind of like in all the spy movies are like, hey, synchronize our watches. It's basically what we're doing here, so that we could be on the right frequency at the right time.
And Jade, there is one question here, and the question is, do the individual radios have to be synced with each other with the hop table?
They do that when they first link in. So how Banner does it is we basically store the serial number of the main unit inside of all the nodes. And when they first power up, they go, hey, the gateway goes, I'm gateway such and such. We're using this hop table. And then the end device says, oh, okay, I'm node 1. I use this portion of the table. Does that clear things up?
Yes, thank you, Jade.
Yep. So in the multi-hop system, We actually have another requirement, at least for the banner ones. This is the tree topology. We require a Modbus master, so the entire tree topology is set up via on the Modbus standard. So that allows us to actually send Modbus commands throughout the entire chain in this case. So we can actually talk to HMIs and other Modbus devices off the end and use that protocol throughout the entire network. So what that allows us to do is we get the communication from, say, a Modbus PLC into our master radio, and it transmits it to a repeater. It'll actually compare what it got inside of it versus the CRC inside of there and make sure everything got transmitted wirelessly correctly, so that we can ensure that the Modbus command goes throughout the entire network correctly. And in these sorts of networks, the main master radio will be your initial location. So you'll want to always have like the main PLC attached to that, so it can send commands into the master radio, and the master radio knows via a table that was formed how everything was linked up. So it goes, oh, I'm the master radio, I'm connected to, say, devices 13 and 14, and device 14 might have 15 and 16 off of it. So it kind of has a little table of how everything's linked together, so that it knows that, okay, this command needs to go to 15, which jumps through 14. So that's kind of how it routes all the traffic through it. It knows where everything's located, and the radios will take that in. Only the radios that it wants to communicate to will get that information and transmit it further down the chain. So you're not kind of wasting bandwidth going to down multiple tracks. That's kind of the bonus of the tree topology system.
Jade, there was a question going back,
Sure.
and maybe you're getting ready to answer it as I see that. The question was, can the frequency hopping spread spectrum be used as a way of security?
Yes. Okay, and that's we're going right into that, so that's perfect timing, actually. So as I kind of mentioned just a little bit at the beginning when we were talking about protocols, there's two different approaches. The one approach is to use a proprietary protocol, and the other one is to use a standard protocol, but basically encrypt it. But along with that is basically using, at least everybody uses frequency hopping, since we're only on a specific frequency for a very short period of time normally for these industrial radios. If someone was using a traffic sniffer to see what was going on in the 900 megahertz or 2.4 gigahertz bandwidths, what they'd see is basically a little blip of information coming on, and it would basically look like background noise for most of the time to most people. That's kind of one of the really good things about frequency hopping is unless they figure out the exact, basically get your hop table, which is pseudo-random inside of the, usually the master unit that's kind of going up. It's very hard to track what's going back and forth over the lines. It gets even harder when you're doing it, if you're doing it in our star topology system where we got TDMA and frequency hopping at the same time, because now these nodes are only on for short periods of time and you don't know which node it is, more than likely, to get that information going back. We're also usually in the wireless security doing network isolation. So basically what that means is we're basically isolating each network from each other. So, in our case, if we got the star topology and the multi-hop, they're totally separate systems from each other, and they're going on at their own times, depending on when they were powered up, basically. And you're seeing the signals going back and forth, but there's no way to really interpret, which system is which in there. And kind of the biggest point of this is most of the time in the industrial radios, as I mentioned before, we're sending analog and digital values back and forth. So when the end device is telling you, say, like your pressure or your tank, how much is in the tank, or you might say the PLC might be outputting a digital pulse every time it finishes a part, and then we transmit that back to a central location that keeps track of it for like OEE purposes. That's all just digital analog values. Most of the time when people are worried about security, they don't want malicious packets getting in there. So if someone tried to insert a malicious packet, say, into our stream, if they somehow figured out all of the frequency hopping and the proprietary protocol and all of that, we can't actually route a malicious packet. It's just going to be like a digital value or a discrete. It's going to say, hey, this word, if you're thinking, or register, depending on how you want to think about it in computer terms, is going to be like 16,000. If it gets modified, you can't actually, the hacker can't actually get in there and all of a sudden start routing people's credit card information or whatever. It's just going to say, hey, now it's 16,000 or 12,000 in that case. So that's kind of the biggest thing for most IT people is, hey, am I ever going to get like a malicious packet routed through the system? And that's just not possible normally for these industrial radios. And the other thing that usually comes up is there a way to like log in or an access port throughout the wireless network? And again, that kind of goes into it. We're not really running a standard operating system in the back of there that will allow those sorts of things to kind of go throughout the network. The other thing that usually comes up is in the security, kind of more of an IT issue, is is my Wi-Fi going to be affected in the plant? And for these industrial radios, usually we're on for such short periods of time that it's not really going to affect the standard Wi-Fi going on. So we just transmit small little bursts of information throughout it. And due to the certifications in the 2.4 gigahertz bandwidth, all the devices are supposed to work together and reliably communicate in the presence of other devices. So along with our frequency hopping spread spectrum, where we're only on certain bandwidths and we're only on for short periods of time, that allows us to make sure that we're not really hogging up any channels or anything, and we allow the Wi-Fi or the 802.11 to work seamlessly with us. Most of the time, if the IT actually was looking there, again, they would just see, like, we'd look like little background noise. And you really don't have to worry about it for most things. But the only thing you really have to worry about is if antennas were really close to each other, then you might get some interference that way. But for most point, where the radios are is right next to the equipment, and then the Wi-Fi routers are probably up in the ceiling somewhere, bouncing around the signals that way. So just to kind of see the difference between the 802.11 and the Banner Wireless, we got a power rating of 100 milliwatts on the Wi-Fi, and again, we're using direct spread spectrum. Got 13 channels, whereas the Banner Wireless is using 65 milliwatts, and we're using frequency hopping, and we're actually using 27 channels. So we're basically doubling the amount of channels that we're on. So there's a good chance that we're not using the same channels that the Wi-Fi is using all the time. The next thing that kind of comes up with industrial wireless is the antennas. This is probably the biggest thing that happens because if we're transmitting analogs and digitals, there's just terminals to wire into. But getting the signals from one point to another is the item of greatest concern. So inside of most of the the industrial radios, there'll actually be a transceiver. So it has the options to basically transmit and receive the radio signals going back and forth. That allows us to basically turn on outputs and then get input information from an endpoint back to the central location. So that allows for great two-way communications. And then here's just kind of a little slide that kind of goes over the, how the transmitter converts the electromagnetic energy and then sends it to the antenna, and then it kind of gets the receiver, and then it decodes that back and to get your signal. So when we're looking at antennas, each antenna will be listed with a gain, and that's usually characterized in dBi. So that's just basically telling us the isotropic dipole characteristics for the antenna. So most of the banner antennas will have either a 2 dBi or a 6 dBi strength. And if you wanted to convert between the other type is DBD, you basically just have to convert, add, to convert DBD to dBi, you add 2.14. So if you have a 3 dBd, that's really equal to a 5.14 dBi. There's also another metric that's kind of used when you're actually doing signal quality. That's dBm. So that's kind of a metric of power per, I don't know if it's millihertz or megahertz. That comes up a little bit later. I forget which version it is. But you always kind of want to keep an eye on how strong the antenna is. We'll kind of show what the difference between the dB ratings does to your antenna signal. And I don't know if it's a slide or two here. So it's good to point out that the antennas are designed to operate at a specific frequency. So if you're picking out an antenna, you basically go to there's a lot of like different manufacturers. You can go to like Elcom is one of the more predominant ones. If you go to their website, you want to make sure if you have a 900 megahertz radio, you're looking at the 900 megahertz antennas. Same with the 2.4. So Matt's asking, what does dBi versus dBd mean to a user? So most of the time, like it kind of says here, they'll use the dBi because it's a larger number, so it makes people feel better. It's kind of one of those marketing things. They're basically synonymous with each other. I mean, for most intents and purposes, it's just how you want to label out the information. So got another question from Matt. What makes an antenna 900 megahertz or 2.4 gigahertz? So inside of the antenna, it'll be set up. Basically, kind of the materials inside of it will be set up so it actually is in that frequency, so it pulses at the correct rate, basically. That kind of makes sense, Matt, or?
Yeah, thanks, Jade.
Okay. So there's two main types of antennas. There's omnidirectional and Yagi, which are directional. So right here we've got the omnidirectional. These are the antennas I like to use the most, just because they're basically the easiest to set up. You kind of think of it like a donut. So the wave coming out of it will be like a donut around kind of the pole going up and down here. And if we look at it a little bit better, so here's kind of what the radiation or the patterns that will be in the literature that comes with the antennas. You'll basically see both of these usually inside of there. So Like for our 2 dB, that you get basically kind of a circular, and that's a plus or minus 800 meter range with if we're using a DX80 banner radio. So you can kind of see how the pattern will look like. Now, if we say jump to a larger dB or a 7 dB, what that does is it doesn't really change this pattern. Besides, it'll squish it down. It doesn't actually give you extra power or anything. All that it does is it flattens it out, the curve here. So now you're going to be going you're going to have a much larger range in the horizontal plane, but now your vertical plane changes quite a bit. So if you got large elevation changes, you have to be a little bit careful if you increase the dB too much, because you might actually lose some elevation change if you're not careful. Now, there's ways to get around that. You can basically tip the antenna a little bit. So if you just need to go down one side of a hill or mountain or something, you kind of position the antenna so that now the horizontal plane is kind of now in a different axis on there, and so now you'll be able to push all the way down mountain or hill. That works out pretty good in a system where you're going from the top to the bottom. You don't have to worry about going to the other side. If you're going to the other side, you might have to do some other things. So here's another little couple images of superimposed of the two different antennas. So here you got the main antenna, or 2 dB, and you got the 6 dB here. So you can kind of see the two different styles going superimposed over each other. And also down here, we haven't talked about the Yagis or shown them yet, but here's what the patterns would look like for 3 different styles of Yagi or directional antennas. You can kind of see they only point this towards this direction instead of going both ways. Whereas where the 3 dB, you got a very large, kind of almost a 90-degree pattern going out of here, or it starts narrowing down with a 6 or a 12. Now you can get the furthest range possible out of, say, of a 12 dB Yagi, but the downside to it is now you've got to kind of position it very well. So if you're 5 miles between the two sites and you got two Yagis pointing at each other, you probably got to use some binoculars or something to help you line them up. And if, say, a storm goes through and it has really high winds, it might actually knock your Yagis out just enough so now they're no longer positioned right, and so you'd have to go back and reposition them. That's kind of why I like using an Omni. You don't have to ever worry about that when you're in outdoor applications. You just basically put them there and then ensure that you get good signal quality between your radios, and everything will work regardless of if a large storm comes through. You can't really knock out an Omni as easy as a Yagi. Now the FCC also will be regulating the strength of these radios. So for a 900 megahertz 1 watt radio, you've got the 30 dBm rating. And actually, a few slides later, I've got all the listings for the various strengths. I think that's actually for a 250 milliwatt instead of a 1 watt. So again, for omnidirectional antennas, higher dB antennas, we're going to have the longer range, but you got to be careful of your distance. Here's what kind of a normal application will look like for a Omni system. So all the radios have Omni antennas. You can kind of see the overlays of how all the various devices are talking back to the central location. But you also got some overlap where they could be connecting to each other if we were in a multi-hop system. So when we're positioning these antennas, it's always best to kind of have them in line with each other. That way you don't lose as much signal between the two antennas. So like in the second location, you lose some signal because some of the bands would not line up with each other. And there'll be a better picture of the bands here a little bit later. So for directional antennas, as we kind of mentioned, they're a little bit more difficult to align. Mounting is super important, and some small changes can basically affect your overall signal strength quite a bit. That's why I like using the Omnis. So we're talking about antennas. We got to basically bring up the Fresnel zone. This is basically kind of your pattern that's going out between the transmitter and the receiver. So we take a little picture here. Basically got our distance between the two units, and then the size of the change. That kind of is based on the antennas. So here we've lost a little bit of the signal when we're hitting those trees. And depending on which type of trees it is, will determine how much signal is stopped there. So like if we're using, if we were going through some pine trees, those actually soak up the signal a lot more than say the deciduous trees or the more leafy trees. Here's kind of 3 different examples. So when we're usually talking about the distance between the radios, we'll always say clear line of sight. So that's kind of what the top zone would be, where there's nothing impeding the transmission going from one point to another. So in the banner radios, when we say clear line of sight 1 watt radios in the 900 megahertz bandwidth, we'll say we got 6 miles of range. And in the top case, we'd be able to get 6 miles of range. In the kind of the middle case, where just part of the signal is getting obstructed, we wouldn't be able to get, say, the 6 miles. We might get like 5.5 or something. It kind of really depends on how much of the signal is being blocked throughout the system. And in the final one, of course, we'd have to even be closer because a good chunk of it is being blocked by that tree. Now, one thing to kind of keep in mind is the worst thing for Fresnel zones is actually going over bodies of water. Any portion of the signal that might hit the water is basically totally diffused. So you can actually lose your signal very easily going over a body of water. Usually to get around that, if you can find like a hill or something else, is you can still get across water pretty easily. You just got to basically elevate higher to make sure that your signal doesn't have a chance of hitting that water. Now, here is the effective system gains. So what we're dealing with is if we directly connect the antenna to the radio, that's normally where our standard system is. So basically every connection in here will be a 5 dB loss. So when we're going from the radio to say this first cable down here, we got a 5 dB loss here and a 5 dB loss here on our antenna connection. So whenever you're doing an antenna connection, it's automatically a 5 dB loss. Another section of loss is cable length. So in this case, we've got 40 feet of LMR 400. We'll talk about the cables a little bit later and what that all means. But as we go through the 40 feet, we're going to have 2 dB of antenna loss just from that. And then here's like say an arrestor, since you got a connection on both sides, that's a 1 dB loss. And then finally we go to the antenna and we got a 5 dB loss for the final connection. And in this case, this antenna is actually an 8.15 dBi increase. So we basically take the antenna and then all of these throughout the entire system to see what our effective gain is. So in this case, the effective gain of the cabling and the antenna is going to be 3.65 dB. So what we do with this number is we add it to whatever the radio can output. So in our case, for the banner radios, 900 megahertz is 30 dB. So the radio will output 30 dB without an antenna. With this system, now we're going to be at 33.65 dB for the entire system. For the 2.4 gigahertz, banner radios will do 18 dB. And to kind of keep in mind, one thing that's not always brought up is every time you increase the gain by 3, you're basically doubling the power of the overall system. And what that allows you to do is basically get through more obstructions or have basically a stronger signal going from one point to another. In a factory situation, what that allows you to do is basically bounce the signal around a little bit more to hopefully get from one point to another, even if there's an obstruction in the way. For every 6 dB, you're basically doubling the distance. So if you can go 1 mile, currently, if you add 6 dB to the system, now you should be able to go 2 miles. And finally, the actual true limits for the FCC. So for the 900 megahertz at 1 watt, the limit is actually 36 dB. And for the 2.4 gigahertz at the 65 milliwatts, the limit is 20 dB maximum. So whenever you're doing your systems, you want to make sure you keep in mind those rules. And the various manufacturers should have that listed inside of their literature. So if you open up a banner radio, near the end of the documentation, it'll say this is a 1 watt radio, 900 megahertz, and it'll say the EIRP limit is 36 maximum. So here's all the various gender connectors. For the most part, Banner uses RPSMA male and female, and then N-type male and female. Those are shown here. The RPSMA will be used on standard cables, whereas the larger cables, which are the lowest loss, will be using the N-type antenna. So here's some coax. Various types. So basically, the larger the wire, the lower the loss it's going to be. So Banner basically uses RG58, LMR 100 and 200, and finally 400. So you can see the LMRs over here. So we're using this one, and finally this small one down here. So for the longest distance cable runs, we always recommend LMR 400. The only downside to that is you jump to an N-type connection. The Banner radio actually has an RPSMA connection off of the radio itself. So you'd actually have to use basically a converter cable to go from the RG58 to the N-type cable, start using that low loss stuff. So you do lose a little bit of gain by doing that, but over long cable runs, you more than make up the loss for switching the genders. So here's a little table for an LMR 400, depending on how far you're going and what your loss would be. So if you're going, we're in the 900 megahertz bandwidth, or 2.4, so we kind of go up in between these, but 900s here. So for every 100 feet, we're actually losing 3.9 dB. So that's something to kind of keep in mind for the longer your cable is. And you can always contact us if you got questions on what you think your cable loss might be in your system, or if you need to do better antennas if you're using a Banner system.
Hey Jade, one question here.
Mm-hmm.
The FCC limit, is that measured out the source, or is that for the combined system?
That's for the combined system. So If we're at 30 to start with on our radio, and the limit's 36, we have to pay attention to the antenna plus all the cabling back to see what the true limit, to what the true system is, and then compare it versus the 36.
Thank you, Jade.
Sure. Now, we're doing outdoor applications. We always got to be kind of a little careful of the radio connections. So we want to make sure that everything's dry and clean beforehand. We connect it, and you'll use basically the rubber splicing tape, and you'll splice kind of around the connection. And then finally, to make sure the rubber splicing tape doesn't get damaged by, say, the UV rays from the sun, you take electrical tape and you go over it too. You need to make sure you start, I think we recommend 1 inch past the splicing tape, and then wrap around it, and probably do it a couple times to ensure the connection is good and you won't get water going into your communications lines. So Banner has a couple of extra features. Some of the other industrial manufacturers have this also, or they do it a little bit different. But we'll go over what the Banner ones are here. So kind of our approach is we want to collect all the various types of information from, say, motors, tanks, analog inputs, or discrete inputs, and then transmit them over to a central location. And then that information either goes into, say, a data collection system, or actually we can actually send it up to the cloud so that the end users can actually consume that in various formats. So we've got various hardware that can actually, we got monitoring and then connectivity. If you just want to focus on monitoring, that's possible. Just get that hardware and then just use either Ethernet IP, Modbus TCP IP, or API commands over Ethernet to gather the information into any system that you want. We're also working on Profinet and MQTT from our devices. So those are kind of future items that are going to be out here shortly.
Hey, Jade, there's a couple questions here. One going back to the lightning arrestor. The question is, instead of a lightning arrestor, what about doing 3 loops of cable near the antenna to prevent downstream damage?
I know people have done various things. I would always look at whatever the local requirements are for that sort of stuff, and see what's recommended. I don't have any knowledge on how, what those loops would be, or if that's what feasibility that is.
Thanks, Jade. And one more question: does Banner offer path studies?
Oh, you mean like frequency studies? Is that what we're asking about here?
I think more maybe frequency studies, but also a path study for a robustness of the network standpoint.
Sure. What we normally do is, if you're thinking about installing a system, basically the next slide kind of goes over this a little bit, but each of the radios has a monitoring device, a monitoring sequence inside of it. So we recommend when you're first, before you actually install any true hardware, is to contact a Banner distributor, such as Gilson, and they can get you a set of test radios. And what you do is you put those test radios into what we call site survey mode, and it'll basically come back with like the strength of the signal broken out into 4 different categories. You can kind of think of that like the bars on your cell phone. You've got got green, which is the strongest, yellow, which is like 3 bars, red, which is like a bar, and then there's a category called M, which is kind of you're like half a bar, or if you're floating back and forth. In that sort of case, we call it missed, I think, in here, but it's really the number of retries. So if you're getting like a 10% inside of there, that means 1 out of 10 of your transmissions is going to need another to loop around for the next iteration. So the information will be delayed by a scan, or depending on how high it is, multiple scans. So we always want to make sure that we got strong signal in our systems when we install them, because that ensures that everything will work properly. So having that feature in there is kind of what we always recommend, using the site survey capabilities of the radios to ensure everything's going. And in the star topology system, you can actually, the PLC or whatever's connected to it can be doing site surveys, getting the information at the same time you're collecting data. So you just say, okay, do a site survey to this. You'd have to wait a little bit of time, because what it's doing is it's transmitting 100 packets, and it's seeing how many of those 100 packets come back. So usually it takes about 10, 15 seconds to get 100 packets going through there while it's doing everything else. And then you can actually get, results and store them, collect that information too, if you wanted to, into your collection system.
Thank you, Jade.
Sure. So the other kind of feature we have is binding. I kind of mentioned this just a little bit, but what we do is we put the main radio into binding mode, and what it's doing is it's broadcasting its basically its serial number, and then all the end devices you want just to talk to that unit, you put them into binding mode, and then it'll go, okay, the two will link up and says, I'm gateway such and such, and he goes, I'm a banner node, and I'm in binding mode, so I'm going to link to you, and then it'll store the serial number inside of itself. So when it's powered down and then powered back up, it'll only talk to that radio that it was connected to, or that was bound to. That allows you to have multiple systems in the network, or in your factory or any location, and the nodes will only talk to the gateways that it's been bound to. So that ensures that you don't get multiple things going where they're not supposed to. And you can kind of think of it like pairing your Bluetooth headset to your cell phone or any Bluetooth device. So here's the site survey that I was just talking about a little bit before. Here, the limits here kind of basically tell you how strong the signal is. So if we're getting the green, we're basically 90 dBm or greater at the receiver side, and it's all broken down here. What we usually recommend is no more than 20% missed, or 1 out of 5. That ensures that 3 scans is going to be enough time to get the information back, 99.9% of the time. But if you got really important information that you want to make sure gets back there, then you might want to make sure the misses are a little bit lower. Usually on these systems, we say, hey, if you can get the information in a second, in 1 second, you can actually have the miss even a little bit higher. If the miss are a little bit lower, yeah, then you might get it in half second, quarter second, or I think the fastest possible is with some safety factor in there is probably like 185 milliseconds with only a few radios attached to the gateway. So it really depends on your how quick the information needs to get from one point to another. But the stronger the signal, it's always the best, because if you change something in the factory or something changes outdoors slightly, you don't have to worry about it, because you got enough signal strength to allow for a few extra packets to be missed if things change slightly. I think about the most drastic thing that ever happened is a guy installed his system, had multiple buildings over a lot. Everything worked fine for like 3 to 5 years. And then all of a sudden they put up a new building and didn't get signal from the one spot anymore. So he had to just raise the antenna up a little bit higher on the 2 spots to be able to get the signal going through. So it usually does take quite a bit of interference. I usually say, about 3 concrete walls isn't going to be a problem if there isn't too much piping in between them. But again, we always recommend doing the site survey to ensure that you're going to have good signal going between the 2 spots.
Jade, a couple more questions here.
Sure.
One is, what diagnostics are available?
So depending on if you're in the banner star or tree topology, The star topology has one specific register that is set up as kind of like our status. So if it has a 128 in it, that means that you're communicating to that node. The gateway is able to see packets go back and forth. If it has a 13569 in it, or almost any odd number, is going to be an error of some sort going to that device. 13569 just happens to be the most common. Don't ask me why it's 13569. I'm sure there's some engineering reason, but it's figure just a 0 or 1 would have been easier. But that 13569 means that you were connected to that radio, but you've lost connection to it at some point. And that number will switch back to a 128 when that communication has been relinked at some point. In the tree topology, we actually use since we're sending Modbus commands through it, we just use the Modbus error timeout portion of the protocol to signal that we weren't able to get the information from the starting PLC or radio to the end device. And usually in the background, we kind of, like in the tree topology, we'll try and send it out at least 3 times. And if we don't get anything back, then it'll generate that error timeout on the Modbus side.
Very good. Thanks, Jade. One more question here.
Sure.
Can you do firmware updates over the air?
In the tree topology system, you can. That can be updated remotely. It's a little slow if you're not directly connected to it. The star and tree topology, you cannot. That has to be sent back to the factory for update. The only caveat to that is the DXM radios units, the control systems. Those can always be updated if you have an Ethernet connection to it.
Thank you, Jade. That's all for now.
Sure. And here's just a couple quick applications. So here we've got an install where we're monitoring a fan. This was actually at one of the buildings here in Minneapolis. The unit was just brand new installed. We put these units on it for monitoring purposes, and you can kind of see in the graph down here where it kind of spikes up. We noticed something was happening there and called the company that did the installation or did the or who did the servicing. And originally they thought it was a bearing issue, so then they just replaced the bearing. But you'll notice that it kind of only went down just a little bit. There was still something going on here. So came back again, and this time they actually pulled it fully apart, and they found, it's a little hard to see in here, but you can kind of see how there's some of this weather stripping stuck in the inside of it. So Banner has some what we call the QM42 VT1s or VT2s. Those are basically vibration and temperature monitoring devices that work really good on mid to large size assets, as long as it makes sense to kind of keep track of them. We've had people put these on conveyor belts too, to see when the conveyor is running and some of that sort of stuff too. So it's really good for monitoring those sort of assets to see when they're starting to kind of get above limits and when you should do some preventative maintenance before they catastrophically fail and cause lots of problems in that sort of case. Much easier to change it out before the motor catastrophically fails and damages a bunch of stuff around it. And then you don't have to replace quite as much. Got a tank monitoring application here. So you got to see the 2 tanks. And so what they were doing before is gravity feeding down into the 55-gallon drum. But sometimes they wouldn't catch when it was full, and then it would basically overfill, and now you got a big mess everywhere, and they got to clean it up. So now by putting some monitoring devices on there, basically a Banner ultrasonic, once it got to the correct level, the wireless unit would say, hey, stop the fill, and then actually tell someone that it was full also, so they could go over there and get that tank and move it to where it needs to be. Another application was a call for assistance here. They were basically printing on material for making chip bags. And after the roll was all printed, they need to run down and scream at the, or scream until they could flag down the fork operator. So by installing some Banner Wireless, now the operators hit the button when they needed the roll taken. Little box on side of the fork system here would light up. They'd press the button, and now it would change lights on both systems saying that, hey, the fork truck operator has acknowledged that it's got a request at line 1. So in this case, they had 6 lines, so there's 6 buttons there. And there's also a central light that would say, hey, one of the lines needs something. So that was kind of more in a central location so that the actual manager could actually see what was going on too. So this actually improved everything. So basically the material got moved around a lot faster and everybody was a lot happier and not getting a sore throat trying to yell down the fork truck guy. And I guess the final kind of application here is we're doing humidity checking here. So when they were making these guitars, they were making sure that the humidity stayed between a specific value. So it was controlled in the overall system. This kind of comes into case here, or greenhouses, or in certain warehouses where the temperature needs to be controlled. You put a couple of these probes around just to do some extra calculations and record and data collections. We've also put the temp and humidity inside of an electrical cabinet that has is temp controlled. So it's got a really expensive cabinet. It's nice to know if the cooling system is actually working inside of it or not. So that's also an application that we've done. That's the end of the presentation. If there's any more questions, I can answer them. Otherwise, I'd like to thank you for taking the